Hi, I'm Seung-Chul Han, master's course student at Gwangju Institute of Science and Technology. Let's begin the presentation about acceleration of three-dimensional device simulation with the 3D convolutional neural network. This work was supported by the NLF of Korea and IITP granted funded by the Korea government. The presentation consists of four parts: introduction, neural networks, result of MOSFETs, and conclusion. Introduction. Recently, the artificial neural networks are widely adopted. Also, the semiconductor industry is no exception. As in the study on the left, artificial neural networks are used for hardware design like the chip floor planning. On the other hand, the neural network applied compact modeling study on the light visual predicts the device properties using the device instance and bias. In device simulation part, there are various attempts. This study applies the artificial neural networks to predict the device properties by using simulation result. The neural network predicts the threshold voltage of silicon junctionless nanowire transistor using off current, on current, and sub-threshold slope. These studies apply the artificial neural network to generate the output characteristics of the device with the device instances. Lab study shows that the neural network predicts the IV characteristics of each device with the device instance and proceed the design optimization with the predicted IV characteristics. Light study show also predicts the device properties with the device parameters about quantum transport device simulation on ferroelectric tunnel junction by using machine learning techniques. These approaches have low cost and high speed, but there is controversy about their accuracy guarantee, since the physical equations are not solved after prediction of the device properties and internal physical quantities such as electrostatic potential, carrier densities are not considered. In our approach, the artificial neural networks predict the internal physical quantity instead of the device properties. If the predicted internal physical quantity is close to the solution, we can use it as initial guess of simulation. Instead of the bias lamping procedure, the predicted initial guess will be provided to the device simulation. Since the physical equations are solved after the prediction, the accuracy can be granted. In our previous work, we applied these approaches to two-dimensional planar MOSFETs. About 2D problem, we use 2D convolutional neural network structure. Left figure shows entire procedure of the previous work, and figure on the right row shows an example of predicted electrostatic potential profile and its error. Figure on right upper shows the Newton iteration comparison between the conventional method and our proposed method. The number of iterations with our proposed method was smaller than the conventional method, about 11 times. About neural network. In this study, before we applied the machine learning techniques to 3D planar MOSFETs, the key internal physical quantity with the neural networks generate should be considered. Under a fixed electrostatic potential profile, the electron and Hall continuity equations become linear or at most locally nonlinear. Therefore, we select the electrostatic potential as target of training output and add the procedure of Frozen field simulation to get approximate carrier densities between the neural network and the device simulation. The neural network can only generate the tensor grid mesh that have fixed number of points. To predict the electrostatic potential profile of the device, the position of each point in the potential profile should be controlled by the device instance parameter. Its example can be shown in this figure. When the gate length is increased, the distance in x-axis between each grid point are increased. In case of gate width, the distance in y-axis is increased. Unfortunately, the tensor grid generated by the neural network cannot be compatible with a general device simulation. General device simulator uses the unstructured mesh for the device simulation. Therefore, we should convert them for each step. For training step, we should provide the electrostatic potential profile solution to the neural network as tensor grid form. The sampling procedure to this. In the neural network inference phase, the neural network should provide the unstructured mesh form matched to the device simulation. Therefore, the interpolation proceeds to convert the tensor grid to the unstructured mesh. To generate the three-dimensional electrostatic potential profile, we select three-dimensional convolutional neural network structure. It consists one fully connected layer and five 3D transposed convolutional layers. Also, its inputs are the 11 device parameters, and its output is the three-dimensional electrostatic potential profile. On the consideration of frozen field simulation and mesh compatibility, the overall procedure is decided. To train the neural network, the training phase should be preceded. In training phase, the device simulations generate the electrostatic potential profile of each device instance. The device instance parameters are provided to the neural networks as input parameters, and the simulated electrostatic potential profiles are sampled and provided as output part of training set. At inference phase, the neural network generates the approximate potential profiles as initial guess of the frozen field simulation after interpolation. Then the approximate potential profiles and the carrier densities produced by frozen field simulation are provided to the device simulation, and we can get the solution. About hardware environment, for neural network, we use four-way graphing units for training and only CPU for inference. In case of simulator, it also uses CPU only. About software, we use Python with PyTorch for training and C++ with the libtorch library for inference. In case of simulator, we use our in-house code GDevice and applied mobility models are inversion and accumulation layer mobility model and high field saturation mobility model in this study. 3D MOSFETs neural net applied. First of all, we considered its parameters which control the device template. The length control parameters are gate length LG, gate width WG, oxide thickness TOX, trench length LTRC, trench depth DTRC, trench width WTRC, and source drain junction depth XJ. The doping density control parameters are source drain doping density NSD and substrate doping density and sub. Finally, the bias control parameters are gate bias VGS and drain bias VDS. These control parameters will be provided to the neural network as input parameter. At training phase, the training data set contains 1000 instances. Adam optimizer mean scale errors and customized learning rate decay are applied for the training. Left figure shows the distribution of each input parameter of the training set. It shows the randomness of input parameters. Right figure shows the training and validation loss graph. It shows there is no overfitting or underfitting. Since the structure is three-dimensional, visualizing the entire potential profile is not very convenient. Instead, quantities on a two-dimensional cross-section are drawn. Left figure shows the numerical solution of this example device. Central is electrostatic potential profile generated by the neural network, and right is error between them. Let's see the longer gate and deeper junction depth case. Also, there are length parameter variations of xj and lz. The neural network can predict the numerical solution profile well. The maximum absolute error in these two cases is as large as 0.36 volt, which is not legalizable at all. Nevertheless, they can serve as good initial solutions to accelerate the device simulation. Conventional method which has bias lamping procedure should spend return iterations each bias lamping step. However, our proposed method can skip bias lamping and requires only one step for conversing. Therefore, expected speedup can be calculated as shown. This figure shows the distribution of the number of return iterations when the proposed method used with test dataset. In the comparison of average return iterations, our proposed method is smaller than the conventional method about 10 times. It means that the proposed method can accelerate the device simulation. Conclusion. In this study, we can accelerate the three-dimensional planar MOSFET simulations by applying the neural networks which can generate the initial profile. Also, our proposed method can provide accuracy guarantee by the device simulation after prediction. The sampling and interpolation capability enables us to connect the tensor grid and unstructured grid. Thank you.